Hello, welcome back to the GeoAI Lab series. In today's video, we are going to explore semantic segmentation for building footprint extraction using the DeepLabv version 3 Plus and TorchGeo. The DeepLabv version 3 Plus also is combined with ResNet 101 backbone. Okay, so why the focus on DeepLabv version 3 Plus? So the DeepLabv version models were introduced by Google researchers. The DeepLabv version 3 Plus combines an encoder and decoder design. Okay, this also has got the Atlas convolutions or the dilated convolutions. So these are very important because they give power to analyze both the local fine scale features and the coarse global scale features. Right, we are going to use the Atlas spatial pyramid pooling to process the mount scale features and the refined coder that is also going to help us enhance the boundary localization for our building footprints. Right, so to start, as usual, we are going to set up our environment. So we start by installing the required libraries that don't come in Collab, and then after that we are going to import all the libraries that we are going to use for the tutorial. So remember, we have done this in the previous lab tutorial. Then after that we are going to mount Google Drive so that we have access to our datasets. As in the previous lab tutorials, we are going to use the orthophoto image and the building polygons. So these are building polygons, they are rasterized. And then after that, we are going to create a custom dataset. So here we are going to take in the orthophoto image and mask, and then we are going to resize them into patches of 256 by 256, and then we make sure that we prepare them so that they can be saved as torch tensors. Next, we are going to split this dataset into training and test dataset. So 80% is going to be used to train the model, while 20% is going to be used to validate the model. And then let's just display the sample orthophoto image and the corresponding mask. So this is what we have, 256 by 256 patch of the orthophoto image and the corresponding building mask. Okay, so next let's go to the exciting part. So here we are going to initialize the DeepLabv version 3 Plus. So we are going to load ResNet 101, and we are not going to use any pre-trained weights, so that's why here I have specified none. And then the number of classes we have is 2, so that is the building and the background. For the optimizer, we are going to use Adam, and we are going to train the model using the cross entropy loss. Right, so before we go to the training, I just want to explain briefly about this model, this DeepLabv version 3 model that we're using here. Right, as I said, we are going to use the Atlas spatial pyramid pooling here, so that it helps the network recognize objects of different size within an image. So what is the difference with the previous approach? So in the previous approach, when we used the unit model, we just used the standard convolution. Okay, so the standard convolution was just like, for example, a 3x3 convolution. And the way it works is that it takes in the first part of the image. Say for instance, here we have these pixels which are covered by the kernel. So 1, 2, 3, 6, 7, 11, 12, and 13. And this is our kernel, which is 3x3. So let's take, for example, it is covering this area. And what we have here is that the visualization is we have only these pixels. These are 9 pixels which are covered, but the rest of the pixels, they are ignored. But when we come now to the heteros convolution, here the convolution cover the whole image, okay, the whole input image. So let's take, for example, in this case. So we have the convolution taking the same 3x3 format, but what we have in between are the gaps. So these gaps could be zeros. Okay, so as a result, what the convolution takes is the whole input image as compared to the standard, where it ignores the other pixel areas. So what that simply means is that the convolution here expand the receptive field. That is the area of the input image a neuron can see is expanded, but without increasing any number of parameters or reducing the resolution. So in a way, this is important because the model is going to gather information from a wider area while preserving the spatial precision. So this is just done by inserting gaps between pixels, as we can see. Right, so this is going to result in a multi-scale feature extraction, which may enable better segmentation, especially if we then input image with objects of different sizes. So this is quite important. So we would like to check if this is going to improve our extraction of the building footprints. Right. So what we do next is we are going to set up our training loop, and here we are going to do that with early stopping, and we're also going to track the accuracy. So as usual, we define the number of epochs. So here it's at 20, and then the patience 5, and then we are going to set the training loss and validation loss, and then the training accuracy and the validation accuracy, and then we're also going to go with the model training. Right, as I said here, the most important thing is that we have added an early stopping, which prevents the model from overfitting by monitoring the validation loss. So if the model stops improving for 5 epochs, then the training stops. So this saves time, and it ensures better generalization. Right, so these are the results of the training. So you can see that the model stopped at 9, okay, at epoch 9. Right, so following that, we can load the best model, and then we can also plot we can also create the plot showing the the training loss and the validation loss, as well as the training accuracy and the validation accuracy. So these are the plots that we produce. As we can see, training loss is decreasing, while we have changes in the validation loss. So as soon as the validation loss starts to go up, then the model stops, so that this prevents overfitting. So the same situation that we have here, we have the training increasing the training accuracy, and also we have changes in the validation accuracy, but as soon as it drops, then the model stops. So this prevents overfitting. Right, so we are also going to compute other metrics using unseen data, so the test data. So here we are computing accuracy, the IOU, which is the intersection over union. Remember, we used this metric in the previous video tutorials. So here we can see accuracy is quite high, but the test IOU is around 82% compared to 97%. And we also are going to evaluate the dice coefficient and the boundary IOU. And if we run this code, we also see that the dice coefficient is quite high, with about 89%. But then when we look at the boundary IOU, it's quite low. It's 28%, which is very low compared to the previous pre-trained unit model, which had around 52%. So there's a huge difference here. Okay. Right now, next we move on to the inference of the full image. So just instead of just predicting on small patches, we can scale this up. So we split the full image into patches and then run the model on each of these patches, and then we are going to stitch the result back together. So this is going to give us a seamless prediction map for the entire area. Okay, remember we trained on small patches measured 256 by 256. So following that, we are going to convert the predicted masks into polygons. So the polygons, we can save them into our Google Drive. And also we can regularize the polygons, so that we remove these noisy edges, and then we can transform the outputs into the clean and mappable building shapes. So this is quite good if we are going to use the polygons for urban infrastructure monitoring or for planning purposes. So you can always compare the original predicted polygons and the regularized polygons. So this is very important. Okay, then next we are going to visualize the model prediction and also the reference building mask, so that we have a clear visualization of the model performance. As you can see, the model also is doing very well in predicting the presence of the building, but the boundaries, they are not quite good. So we have problems here with the boundary of the buildings. Okay. So this is a major issue. So no wonder why the boundary IOU was very low. Right, next you can save the model so that you can use it for your future use. For example, if you want to run the model again and improve it, or you want to use the model for inference purposes. Right, finally you can generate an automated report that summarize all the key metrics and also the file paths and then the performance statistics. So this is good for reference purposes. Right, so this is all about today's tutorial. So in summary, in this tutorial I show you how to perform an end-to-end deep learning with the DeepLabv version 3 in TorchGeo. So this is a very important deep learning pipeline that you can use for your geospatial task. So we have looked at pre-processing and patching to post-processing and reporting. Right, so please drop comments if you want me to cover other geospatial tasks for Earth observation, for example, road extraction, flood mapping, and other tasks of interest. And don't forget to check the video description for the full code and our course catalog at Ai.Geolabs. And next week we'll be announcing the date for our webinar and the training workshop. So thank you very much for watching. I will see you in the next lab.